This lab is called Boyle's Law, relating the volume of pressure and gas. It's experiment number 9 in the CHEM 1050 lab manual. Boyle's Law relates volume and pressure. This is an inverse relationship. So volume is inversely proportional to pressure. And this is how we would mathematically write that relationship. Where if the pressure is getting bigger, the volume is going down for gas. If the pressure is dropping, the volume will be increasing. You're going to have a setup like this. So you're going to have an enclosed volume that consists of this syringe and this flask. Inside the flask, there's going to be some water. There's a tube here. The tube is open to the atmosphere. So here's the concept. Your flask will have a tube. The tube will be beneath some water. You have a syringe over here that's going to adjust the volume. So the atmospheric pressure pushes down the tube because it's open to the atmosphere. And so long as the pressure here inside the flask equals the atmospheric pressure, your water level in here will be the same as any water level that's in the tube. Keep the tube look. So you'd see something like this, okay? Now, if I close the syringe, volume, it's gonna drop my volume so that my volume is decreased. So I'm gonna have a volume 2. So pressure 1 will be the pressure of the atmosphere. Volume 1, we're going to go ahead and measure. Volume 2, we're gonna diminish by closing the syringe. So volume 2 will be less than volume 1, okay? So we had a pressure, it was atmospheric pressure. We had a volume that was the total volume of everything. Now we diminish that volume. What's gonna happen to the pressure? Pressure 2 will be greater than pressure 1. How are we gonna see that? Well, we have the atmospheric pressure pushing down the tube. If the pressure inside gets greater than atmospheric pressure, it's gonna push on the surface of the liquid, just like atmospheric pressure pushes on the surface of a liquid that you're drinking through a straw. This will push the liquid up the tube, and the height of the liquid up the tube will be proportional to the pressure difference between the atmospheric pressure and P2, the pressure inside the flask. So the stronger P2 is compared to the atmosphere, it's going to push that liquid up the tube. Okay, so using this relationship, you're going to set up a table. You're going to solve for the pressure inside the flask. You will also know the volume inside the flask because as we go through the steps, you're going to measure that. Now, there is a flaw in this experiment. We're going to be measuring the volume inside this flask, but notice that some of the water is going to be going up the tube as we decrease the volume of the flask. When this water goes up the tube, this water level is going to go down slightly, right? When that water level goes down slightly, it changes the volume compared to what we think it is. So our numbers are going to be a little bit off because we're not accounting for the loss of the water inside the flask, which is going to slightly increase this volume. So what you're going to notice in your data, you're going to be calculating P's times P's times V's at different adjusted volumes. You're going to see that this is not going to be exactly constant. And typically what you see is it drops a little bit, but not a lot. It's going to demonstrate Boyle's Law pretty well to you, where you're going to see the consistency of the P times V product. But a little bit of experimental error because of this small flaw. So keep that in mind as we go through the experiment and you process your data. Here's the experimental apparatus that we're going to use to measure the pressure-volume relationship for a gas. This will enclose our volume. The way we'll change the volume is by changing the volume on the syringe. So the first thing that we are going to do is measure the volume that's inside this filter flask. So the way we're going to do that is we're going to fill this filter flask with water. We need to fill it up to the top, and you also want to fill in the side arm until it's completely filled with water as well, but don't fill the syringe itself, because that volume is listed on the side, so we already know what the volume of the syringe is. So we'll fill it all the way up. I'm going to draw some air or some water into the side arm to make sure I got that filled with water as well. Top it off. Now, when the apparatus is completely assembled, there's a rubber cork in the top, so that takes away some of the volume that the air can occupy. So I'm going to put a rubber cork in there to displace some of the water, and that'll be accounted for as volume that the air is not going to be able to occupy. Now I'm going to measure the volume that the air can occupy by measuring the water in this graduated cylinder. Now this graduated cylinder only goes up to 500 milliliters. So there's probably more than that in this flask. So when I get to the 500 milliliter mark, I'm going to stop. And then I'm going to go ahead and dump out the 500 milliliters, knowing that that's part of my number, and then pour in the rest. Then I'll measure out what the rest is. So looking at the side, 90, it looks like it is 75. So I had 500 milliliters. To that I add 75 milliliters. So the total volume in the flask, without accounting for the syringe, is 575 milliliters. So that value goes on line 1 in your report sheet. All right, now the next step is we want to account for the volume that the tube is going to occupy when you put it into the flask, because the tube occupies volume that the air is not occupying when it's in the flask. So we have to know the volume of this tube. The tube is a cylinder. So to calculate the volume of a cylinder, you need to make two measurements: the length of the cylinder and its diameter. Actually, what we really need is the radius, which we remember is half the diameter. So let's measure those. I have a ruler here that I'll use to measure the length in centimeters. Oh goodness, here we go. And that's going to be 15.80 centimeters. So the length of your tube, so this is line 1, the length of your tube equals the 15.8, and we can estimate one more digit because it's marked to the nearest millimeter. Looks like it's right on the line to me. So 15.80 centimeters is the length of the tube. For the diameter, we use this fancy micrometer gauge to measure the diameter. And I'm just going to go ahead and measure that for you without explaining how this works, because it's a little complicated to do over video. So that's going to be, the diameter would be 0.78. So the diameter is 0.78. Centimeters, so you know that the radius would be this 0.78 divided by 2. So you should be able then to calculate the volume of this tube. And if you look at your data sheet, The volume of the tube would be listed on line 4, and you'll see the formula, length times pi r squared, to calculate this volume. Now, to get the volume of the air in the flask, we have to take into account one more thing. Remember, in my first discussion, we said that there's going to be water in the flask, and the water will then be pushed up the tube as the pressure increases inside the flask. We have to add 50 milliliters of water into the flask in order to accomplish that. There we go. So we add the 50 milliliters of water, and then we're going to go ahead and set the apparatus up. You have to make sure, here I want to show you something real quick. So when I put the tube in, I have a set volume. When I push down on the tube, on the cork, you can see a little of the water level come up. I don't know if you can see that or not. Let me try that again. So that means that as I put the cork in, the volume's decreasing inside the flask. Therefore, the pressure's increasing compared to atmospheric pressure, so it pushes some of the water up into the tube. To determine the volume that's actually in the flask, then you have to take the entire volume of the flask, subtract off the volume of the cylinder, and then subtract off the 50 milliliters of water that you have in the flask. So when you calculate this through, you'll see for line 5, it tells you to do that. So you will go ahead and subtract the line 4, and then you're going to subtract another 50 milliliters because of the 50 milliliters of water in the flask. Now the other item that you're going to need to know is the atmospheric pressure. So you'll see line 6 asks for the atmospheric pressure. So we have a barometer here in the classroom. Let me go see what it says. It says the atmospheric pressure is 29.59 inches of mercury. Now that's inches, and it's also measured in mercury as our liquid. And that's going to have some implications for us. So you're going to have to convert that to that 29.59. You're going to have to convert that into centimeters of mercury. So that's simply converting from inches to centimeters, which you should already know how to do. So that is the value that you're going to put on line 6. Convert that inches to centimeters and place it on line 6 in your data sheet. Okay, with all of that, now we're ready to take our experimental data. So I have the filter flask here with its 50 milliliters of water ready to go. So I arranged the syringe so that it is reading at 30 centimeters, and we're open to the atmosphere. So right now, the pressure on the liquid is the same as atmospheric pressure. Now, when I insert the tube, some of the liquid is going to go into the tube because now I'm going to decrease the volume by putting the cork into the tube. So some of the liquid will go right up on into the tube, and I'm going to go ahead and read that. And that reading is 2 centimeters. So the column height C, when the syringe is at 30, is 2 centimeters. So write that in, because I'm not going to write that on the board for you. You have to keep this data as we go. Now, I'm going to have to move along quickly because I don't want any sort of leaks during this process to throw the data off. See if you can see, I know it's a little difficult on the video, but see if you can see the water level rising as I decrease the volume of the syringe. So now I'm going to move the syringe to 25, and the value will go up. And right now, it's at 11 centimeters. So you're going to write 11 centimeters for column C, where it says 25 milliliters for the syringe. Now we go to 20. And at this point, the water level is hidden by the cork. It's gone inside the center of the cork. So that's going to be, I would put down 17, but that value might be a little bit off. but put down 17 for the syringe level at 20. So now I'm gonna adjust the syringe to 15. And there's my water level above the cork again. So now I can read it. Now I have to read backwards. There's a red line up here, right there. There. That's 25 away from a red line that's below here. That's gonna help me count. So that was 10 there. So here's 35. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be 34. Not 34. So 35 minus 10 would be 24. 24.7 would be our level there. So at 15 centimeters, we're at 24.7. So putting it into 10, our level is now just shy of 35. I have to go back 2. So 35, 34, 33, 32. So 32.8 is at the syringe level 10. At syringe level 5, I'm going to be at 35, 6, 7, 8, 9, 39.4. And then closed will be 46.5. So when it's at 0, it's at 46.5 centimeters. So you should have all of your data for column C filled in at this point. Now, to process that data, take a look at the instructions. So column A is the syringe volume, that's set. You're going to take the value that you calculated on line 5, and you're going to add the syringe value to it to get the total volume inside the apparatus. The column height you've read. The column height is going to be proportional to the pressure difference between inside the flask and then the atmospheric pressure that's pushing back down on the tube. So that can be converted to what the total pressure inside the flask must be, and that's what we're going to do. But first of all, we have to have the atmospheric pressure and the pressure that we're reading off of this tube in the same unit. So this is centimeters of water. A barometer reads in the elevation of centimeters of mercury. Mercury is more dense than water, so it's going to push less of a height than water does at the same pressure. So column D, we're going to take our water heights and convert them to what the height would have been if we used mercury for our liquid in this experiment, which would have been very dangerous, so that's why we didn't do that. So to do that, you use the ratio of the two densities. Mercury is 13.6 times more dense than water, so we have to divide the water levels by 13.6 to convert it over to what the heights would have been for mercury. So if you see column D, you're going to take your numbers in column C and divide by 13.6, just like it says. But that's why, because we're converting over to what it would have been if we used mercury. Then the pressure in the flask is going to be the difference between, it's not the difference, the column height rises as the pressure difference between the atmosphere and inside the flask. But we want the total pressure inside the flask. So the total pressure inside the flask is atmospheric pressure plus that pressure differential, which is the height, right? So you're going to add the height. So this is how much more pressure we have inside the flask than outside the flask. So we add the height to the pressure outside the flask, which is atmospheric pressure. So you're going to take your atmospheric pressure in centimeters of mercury, which you've calculated on line 6, and you're going to add it to the pressure values that you have determined in line D to get the total pressure inside the flask. Okay? Finally, once you get E settled, where you've added column D to line 6 for each value, you're going to multiply the pressure inside the flask by the volume inside the flask. The volume inside the flask is in line B. The pressure inside the flask is in line E. So you're going to do that for each value. And you should see a large number. Don't be afraid if the number's large, it's going to be large. And it should be fairly consistent from top to bottom. Now remember, in the intro I talked about the little bit of error that you're going to get due to the fact that we lost water. That 50 milliliters of water that we subtracted off actually gets smaller as the experiment goes along because the liquid goes up the tube. So the volume number is not quite accurate. So therefore you're not going to see perfect numbers here, but you should see numbers that are really, really close if you've calculated everything correctly and I've made your measurements for you correctly. So finish up the table, get your P times V values, and answer your post lab, and then you are all set with this experiment. And in case you had trouble reading the board from an angle, here is the data that was written on the board.